Today's problems are taken from a humongous book of calculus problems. Before we get started evaluating limits, let's try to understand why is it important and also how many different solutions you can get from evaluating limits. There are 8 different cases. The first one is finite limit, where your limit is equal to a number. If the limit of a function exists and is a finite number, it means that as the input value gets closer and closer to a certain point, the function values approach a specific finite value. The function is approaching the same value from the left and from the right. If this is confusing to you, no worries. The examples will help you, so stick with me. Second case is infinite limits. You can get a negative infinity or a positive infinity. If the limit of a function becomes infinite, positive or negative, as the input approaches a particular value, it means that the function value grows without a bound as the input values get closer and closer to that point. This happens when a function has vertical asymptotes. Asymptote line can be vertical or horizontal. It's a value where your function approaches but never touches. An example of a function with an asymptote is tangent. Tangent has a vertical asymptotes on both sides. Another example is 1 over x. Let's say we're given a limit as x approaching 0 and the function is 1 over x. We cannot plug in 0 right away using substitution method because 1 over 0 does not exist. It should give you undefined. So what is the limit? What does the function approach to? Let's look at the graph of the function 1 over x. The graph actually exists in 2 different quadrants, the first and the third. And we see that as x approaches 0, our function is approaching from the left to a negative infinity, which is going down, and the function is going up from the right to a positive infinity, which means that our infinity, our limit, is approaching 2 different values at x equals 0, which is the asymptote. That is a sign that our limit does not exist. But let's see a different value. Let's say we're given x approaching 2 instead of 0 for the same function. X is approaching 2 from the left and from the right. And we see that our function is going towards 0.5, as we can see here. And also, if we used substitution method instead of looking at the graph, we would get 1 over 2, which is 0.5. Third possible answer, as we already seen, is that limit does not exist. The limit of a function may not exist at a particular point if the function's values do not approach a single value or same value as the input gets arbitrarily close to that point. This can happen when the function oscillates or behaves erratically around the point, just like our 1 over x when it was approaching 0. Fourth case, approaching from different directions. Sometimes the limit might be different depending on whether you approach the point from the left or from the right, as we saw from the example 1 over x. Our limit was approaching negative infinity from the left and positive infinity from the right side. But if the problem was given only from the left side, then our answer would be negative infinity instead of the limit does not exist. Number 5, approaching different values. The limit can also vary for different sequences of paths of approaching the point. This can indicate that the function has a more complex behavior near that point, possibly involving oscillations or fractal-like patterns. The next one, number 6, is intermediate form. In certain cases, you might encounter a form like 0 over 0, infinity over infinity. In these cases, you might use L'Hopital's rules. It can help you evaluate the limit of intermediate forms. Now, I have to assure you that this video does not include L'Hopital's rules because it's kind of its own thing, and I want to dedicate another full-length video on that. Next one is limit at infinity. So instead of plugging in a number, which is x approaching some kind of number, a, we might have a limit approaching an infinity, negative or positive. These kind of problems can provide insights into long-term behavior of the function. As we know, functions represent real things that are happening in real life. So these kind of problems can help you what happens to the function when it grows or decays as the input becomes very large or very small. Now the last one, number 8, is special cases. Is occasionally you might encounter specific cases where the function has a unique limit that requires careful analysis. Examples would be trigonometric, exponential, or logarithmic problems or functions that are given in a limit. Also, these special cases are not included in this video because I want to make it a series and give a full-length explanation, and otherwise this video that you're watching right now will be very long. Now let's get into why is it important, how to evaluate limits, and also how is it used in real life. As we know now, limits allows us to understand and analyze the behavior of functions as they approach a specific value, or as their inputs get arbitrarily close to a certain point. This is where the idea of continuity comes to play. A function is continuous at a point if its limit at that point exists, and it equals to a value at that point. This concept is essential in analyzing the smoothness and connectedness of functions. Also, derivatives. The derivative of a function at a point is defined using a limit. Many functions are not defined in simple algebraic terms, but their derivative can still be calculated using limit. Limits also help us understand rates of change in various contexts, such as physics, economics, and engineering. Many real-world phenomena involves quantities that change continuously, such as populations, temperatures, and stock prices. Limits allows us to model and analyze these changes more accurately. Now let's get into some examples. Here I created a tree, so we will go from the simplest method to the most complex ones. Before doing any other method, you always need to try substitution method because it's the easiest one and it will lead you to the answer the fastest. Let's say we're given a problem that you can use substitution method right away. And the example I have is limit approaching x to -1 of a function 3 to the x. Substitution method is exactly what it sounds like. You need to substitute x for -1. So you have to plug in -1 where you see. When we do plug in, we get 3 to the -1, which is equal to 1/3. What if we are given a problem that we cannot use substitution method right away? The next method is factoring. And this is the example we're given. Limit of x approaching 0 of a function 4x to the 5 minus x squared over x squared. And the reason we cannot use a substitution method for this problem is because x is approaching 0 and our function is a fraction and we cannot have 0 over 0. This doesn't tell us anything about what happens when x is approaching 0. Again, we need to factor because this is a factoring method. I'm going to factor out x squared and we will have x squared, and in parentheses we have 4x to the 3 minus 1. And it's also all over x squared. So our first step was to factor. Now we need to cancel out. We can cancel out x squared from the top and the bottom. Now that we have successfully eliminated the denominator, we can use our substitution method right here. Let's plug in our x, which is 0, and we will be left with -1. So to recap, we had a problem. We had a problem that the denominator cannot be 0. So now we know that the problem area is the 0 on the bottom. We need to get rid of that problem, and we did that by factoring. What happens if we cannot use substitution method and also we cannot use factoring method? Then our third method that we will learn today is conjugate method. Conjugate means that two things have the same real parts but opposite in sign. And this is the example. In this problem, you cannot really substitute and you cannot really factor. There's nothing to factor here. The problem is our denominator, square root of x minus 4. And the conjugate of that is square root of x plus 4. Same real parts, but different in sign. This is what I mean. But we need to have, we cannot change the actual problem itself. So we want to multiply it by 1. And to make it a 1, we will have the same part on the top, on the bottom. And that's literally equal to 1. Now this is a difference of squares formula, which will give us square root of x squared minus 4 squared. And that will basically be equal to x minus 16. And we see that on the top and on the bottom we have the same thing. So that means we can cancel it out. Now this is very similar to our factoring method where we canceled out something on the bottom and we were left with a simpler problem where we can use actually substitution method here. When we plug in 16 for x, we're gonna get 4 plus 4 and that will equal to 8. Let's zoom out a little and this is what we have for now. So far we covered these three methods, and if they do not work, then you need to go into special limit theorems. And that is a video for another day. And so far we have this tree with examples. Hey, thanks for watching until the end. And I have a blog post about this topic in the description below, and it will have everything I talked about, also more examples and more problems that you can solve on your own with answers too. So check that out, and more blog posts are coming too, and I will also link another blog post about fundamental theorem of calculus, and a next video is on that topic. So stay tuned.